oscillations. In this lab, we analyze a mass on the end of a spring. For the system used, it contains the spring, mass, and earth. This means that we will have potential energy formulas involved, and theoretically, the change in total energy of the system should be zero. We took data points within each frame of the video and used those data points as the experimental data to compare with the created model. We used GlowScript along with several known formulas to try to create an accurate model of the spring and mass system. Within this lab, we used several different formulas pertaining to gravitational and spring potential energy, along with velocity and position update formulas. The first is K equals 1/2 mv squared. Next is UG equals mgh. Next is US equals 1/2 K sub s squared. Then E equals K plus UG plus US. Then VF equals VI plus F net over M delta T. And finally, RF equals RI plus VI delta T. For these formulas, K is the kinetic energy, UG and US are the potential energies for both spring and gravitational, E is the total energy of the system, and then VF and RF are the position and velocity update formulas. And then to the right are the formulas used within the code. After creating the program to create a model to compare with the experimental data, we ran it and created the plot seen to the right. The top plot is the change in energy over change in time. The middle is the y position over time, and the bottom is the x position over time. For all the plots, there has been some error within the code, but overall it is mostly accurate. For the first graph, delta E oscillates slightly when it shouldn't. For the second graph, the model position is exaggerated and slightly misaligned. And then for the third graph, again, the model is slightly exaggerated this time and only slightly misaligned. For the analysis, the first thing to address is the errors. For the change in energy, the reason it is an error is because within the experiment, with how we defined our system, as mentioned previously, there should be no change in internal energy. This was most likely caused by minor errors in data that don't completely match between experimental and predicted data. And then for the position graph misalignments, it could be simply because the data I used was not calibrated properly before being transferred and used within the code. Using the data we gathered and plotted, we can get a rough estimate of oscillation period by analyzing the graphs created for the x and y positions. Based on the x position graph, the period of oscillation is estimated to be about 1.75 seconds from trough to trough, and based on the y position graph, the period of oscillation is estimated to be about 1.5 seconds from trough to trough. So overall, by taking the average, we can estimate the time to be about 1.625 seconds from trough to trough.